backward and laser pointer.
Got it. Okay, thank you very much. I appreciate this opportunity to be here. It's always nice, and the good news is that my mathematics is not quite as tough as some has been before, so that may be good or bad news, I don't know which. I want to start out kind of strangely in a way because this yin-yang symbol, so to speak, it's a satellite of Saturn. It's the moon Epochs. It has one side which is all mostly white and one side which is basically black, which is kind of unusual. It's really the only place in the solar system like that. This is a somewhat better shot of it, closer up, thanks to Cassini, and looks kind of normal in some respects, except for sort of a little ridge running around there, which, as it turns out, shown here, this ridge is well, if it were on Earth, on a relative basis, it would be 60 miles high. It goes all the way around the planet, all the way around the moon. This is extremely strange. There's nothing like it. And there's been some attempts to explain it, but it doesn't get explained too well. Nor does the black-white get explained too well. We just can't quite figure that one out. But, of course, all of them are running around the planet Saturn. Now, as it turns out, most of the moons of Saturn are basically on the same plane as the rings. And so, really, if you're on one of these other moons, you can't see anything. You can't see the rings, just kind of a thick line maybe. Maybe you get a shadow on the planet occasionally, but that's about it. But Epochs is a little different. You can see that the Saturn with all the other moons and the rings are right in here. And then Epochs is doing this really nice ellipsoid here. It's about 900 miles across, and it's got a few things. It's really one of the very few satellites that has a, shall we say, a moon with a view. I mean, it really gets to see Saturn, and you don't get to do it otherwise. And in fact, moon with a view is a good place to go if you're interested in doing this. And looking at this further, it's by Richard Hoagland and some other things. And it's really pretty fascinating in a lot of respects. I mention it at this point because, from my viewpoint, it's my motivation in a way for some of the things I'm talking about doing. And that the whole idea of this talk is that, one, if I wanted to go to Saturn, I'm going to need a good propulsion system, not a warp drive necessarily like that, because let's face it, if we had warp drive, there'd be some rules saying you can't do it inside the orbit of Saturn or something like that. It just cause too much. It'd be terrible. But anyway, I also need an energy source to get there too. And so we're going to do a little bit of a segue here. We're going to talk about propulsion, and we're going to talk about going into developing some energy from all this. Now, what I want to start with on this, in terms of propulsion, is Newton's third law, which is for every action, there is an equal and opposite reaction. Now, equal and opposite is probably to be emphasized because equal and opposite is a conservation. That's right. If you push against something, then we got to have the same amount of push going the other way. Otherwise, it doesn't. Something wrong. But maybe that's not quite right. For example, anytime you have a conservation law, you have to kind of look at all the assumptions that it makes. This one makes, for example, it assumes a point mass. It assumes action upon the entire body simultaneously. We also know in general, in terms of mechanics, that the mass is usually concentrated at the center of gravity. Things act as if they're operating from the center of gravity. Some of these assumptions are essentially assumption of simultaneity, in which you're pushing on everything at once. There also is assuming you're acting upon a rigid body, which doesn't work if you're dealing with Jello. Jello's not generally used in most of these talks, but in fact it does serve a purpose. One of the things that all these laws, Newtonian mechanics in particular, it still works, the mechanics, it does work. When you get into very high velocities, like approaching the speed of light, hey, great, you're going to have to make some changes. But Einstein really just extended Newtonian mechanics into certain realms. And I want to suggest today that one of the realms we need to extend it into is extreme accelerations. Not only extreme accelerations, but extreme changes in acceleration, which is what I'm talking about in terms of a radical change of pace. the basic concept we're trying to generate here is that if you have an initiating force applied to an object, and it takes some time before that object can exert an equal and opposite reaction, then the initiating force, the prime mover if you want to call it, can retract and avoid the reaction. The slide that Mr. Woodward just showed, it was great, I loved it, where he shows one mass kind of bumping into the other mass, and it just moves it all the way down the line. That's kind of what we're talking about, except you're pushing against this mass, and then you get away from it before it has a chance to react. It's almost like if you want to rob a bank, you can do it. You just have to get out of the system before they catch you. So if you're really quick, you go in there, you get the money, and you leave. And of course, the system, has to be the whole country since there's law enforcement, things of that nature. But if you can get in and out, it works. William L. Davis said many years ago, you can get away with anything just as long as you're outside the system before it can react. And I think that's kind of the name of the game, and that's where the propulsion idea comes from, that we push against something and we get out of the way before it happens, then we can push it again. It gets a little confused because then it keeps getting pushed and gets signals in there, but then before it can do anything, you're gone. What we've done here, this is the top equation was one that William L. Davis actually started up with. You have a classical mechanics, all these various things. Oops, excuse me, wrong button. This position, the viscosity, this is basically a resistance term. This is the mass, M equals F equals MA, excuse me. And this is the third derivative. The third derivative is something we're not really using. We're used to force, capacitance, resistance, inertia, whatever, but not so much a third derivative. And it's the third derivative that really counts. It's curious that the electrical circuit has the same kind of form of an equation. There is an assumption here of these two items here, which may be something altogether different. And right now, this is basically a constant, and this would be a mass, but that might not be the same, and it doesn't actually require it to be done that way. This is actually a solution, and I put this up here primarily because to point out the denominator, this term here, which is the inductance, capacitance, resistance term, and then this other term right here. Now, you can get, in terms of, if you're trying to get something really good in a denominator, you don't go to zero. This term here could go to zero. You could have the inductance and capacitance at some point basically matched. Here, if you didn't have this term, if it was zero, you always have R squared. It's always going to be something. You may get some reduced resistance in terms of superconductivity, but it's not going to zero. Here, though, theoretically you can. And so you could have a position where suddenly this thing goes to zero and the charge goes out of sight. This shows kind of going over into power now, our energy, and we get the same kinds of equations. Everything is pretty much the same. Excuse me, again. This is based on charge here, but you can also do it in terms of, well, you can do it in terms of current, so it's slightly different. But I prefer to use this. We're going to keep referring to this third derivative as being the important thing. If you solve the equation, one of the things that happens here is that, well, this is just the rate at which energy is delivered to the circuit. That's your input. This is the capacitance, this is the inductance terms. They're pretty much the same, except especially with the sine term. And that sine term can go back and forth. You can get a plus or a minus with a sine of any angle. Okay? So those two go back and forth. They simply just rotate around each other, if you will. It's the same thing on a pendulum. You have potential energy of a pendulum, but no kinetic. Then it comes roaring down, and you lose potential energy, and it goes into kinetic energy, which is the same basically concept you're doing here. The term for, the term for the resistance, I squared R heating, if you will, it's a sine squared though. So in this term, it doesn't switch signs. Your resistance is always going to take energy from the system and deliver it to the universe, some part. Okay? Well, it's the term that matches it is the term we've added here. This would be the third derivative of the charge. Same thing, but it's the opposite sign. So this third term is basically saying this is the energy. Whoops. Okay. Thank you. This is the energy put in by the universe into the system. It's going the other direction. And I don't have as much time. This is a power ratio, which says sort of the same thing. If this was 0, it would be just this. That's why you don't get overunity, because there's always some losses here. This is always a positive number, and you're always going to have losses. But if you don't, you do something altogether different. Now, the thing that's important here is that this term here, this is kind of your mainstream physics. This is what we've always been operating with. This is what everything's kind of based on, built on. But what we want to do is go to this term here and try to make something of it. Now, this is a quote by Arthur Young, who got into this third derivative aspect. He said the science is based on the derivatives discovered by Leibniz and Newton. I like the fact that he keeps Leibniz in there as well as Newton. The derivatives are rates of change. The first derivative, change of position, velocity. The second derivative is the acceleration. The third derivative is a change of acceleration, or the acceleration of current, either one. That's always ignored by science. But it is because we can change the acceleration that we can drive a car. You know, if you couldn't stop, you push the accelerator and couldn't change that, you might be in somewhat trouble. And this is basically the idea. It is through control we use the laws of determinism. The control is a principle which makes it possible for life in similar fashion to use the laws of determinism to control metabolism, to store energy, and move against entropy. This is the theory of process that Arthur Young put out, and I emphasize it because it's got the 0, first, second, and third derivatives. The first is what he called unconscious action, and then the second, unconscious reaction, and then conscious reaction. These three, again, are the determinism. This is why physics, if you look at the hardcore physics in a way, everything's determined. It's just a clock. We're just running along, we're just trying to get all the details, but nothing can only be added or taken away. But when you go into the third derivative, this control, this conscious action, you change something. So there's even a certain sense that suddenly we have to think about consciousness, which, by the way, we'd probably rather not think about. Not in physics, it's too hard to deal with. What I am trying to say in this very, very brief thing, because I'm just about out of time, the universe always contributes. At steady state, the contribution is probably minuscule. It simply wouldn't show up on anything. Transient conditions yield greater university contribution. One of the things that people have noticed in mechanical engineering is that if you turn on some motors, when you first apply it, you get this transient condition, and before you know it, the thing just takes off and it goes berserk, blows up in some cases, it literally comes apart. They even have to spend a lot of time to make sure the transients don't get out of hand. But the transient condition is the deal, is the change. And the greater the change, the greater the universe's contribution. The greater the rate of change. The system, there's a system delay. If I like I'm pushing against this pedestal here, there's a message goes from here into the center of gravity, and it comes back, just push back. But if I do it real quick, it won't have a chance. And this time delay is the name of everything. This whole thing actually gets shown up a little bit in something called thermoluminescence, most of you are probably familiar with. And this case, this is an ideal place to kind of look for it a little bit, because you're going from an acceleration, billions of times the acceleration of gravity, to zero acceleration and going the other direction. And obviously the rate of change of acceleration is enormous. And when you put some of the numbers to it, it comes out, you start getting watts out of this contribution. And so it's not totally insignificant. And that's being fairly conservative in terms of your assumptions. The big key, of course, is that time delay, that big number, which in this case was either the D or the W. So that's what makes it. But you still need local energy in the system to initiate the reaction. Okay, I'm already out of time. Okay, so if any questions?
Our speaker ended right on time, so we have about 5 minutes for questions. Okay, Bernie's closest.
So I'm just curious, what does this have to do with the moon Iapetus? And secondly,
I didn't hear the first
what
part.
does this have to do with the moon?
Oh, it deals with the moon in the sense of I just want to go there. And we need a manned space mission to go there. So no, I don't know where it comes from.
Okay,
No, I
second
don't.
question. Of course, you can keep going to higher and higher derivatives. Why stop at 3? Why not 4, 5, 6?
If you do the fourth derivative, it's a good question. I like it. I say it's a good question because I actually thought about it before and I have an answer. But if you actually do the mathematics, the fourth derivative, the form of the fourth derivative turns out to be the same as the zeroth derivative. The fifth is the same as the first derivative. And the difference is a frequency to the fourth power. So it's like I think of it as kind of a resonance or a harmonic, maybe that's a better term, of the zeroth derivative, the fifth is, or the fourth, excuse me. So it works out that way in the mathematics.
Further questions?
Okay, then we got to have one over here next because I want to see him run back.
Hey there, I was just kind of wondering, you said you have to push very quickly. Do you have an order of magnitude on how quick you push before it reacts?
The luminescence is an example that at least we have something to do with. About 25,000 cycles per second. So it's a pretty good sized number. If you apply the numbers, it does require some pretty high frequencies, which means we may be limited in some fashion by technology, but it's not limited in principle. But I have seen other things too that this is not completely part of it, but it's also part of the situation. If you've got even any kind of reaction to this, one of the things you would do, you would certainly prove that the law of conservation of energy is somewhat lacking. My own feeling is the conservation of energy is kind of a bookkeeping. That's what we'd use it for, but there's round-off error. If it's only 49 cents, we're not going to count it as $1, and so forth. So that helps, I think, a little bit there. Another question.
You talked about the transients. I remember with some consulting I was doing, we had a 700 horsepower electric motor that was not induction. And we had to tell Kansas Power and Light 20 minutes before we pushed the start button. Otherwise, it would bring down the whole of Kansas. Do you consider the impact load, when you talk about transients, you talking about impact load, or do you include the impact of when you first start something? Because there is an impact load
Yes.
that is greater than the normal load.
Yeah, I think that's actually part of what it is, and I think it's if you include that startup impact, it really, that transient area, a whole lot of things are possible that weren't possible at all before, and that's really, so I'm basically agreeing with you on that.
Other questions?
Can't say anything.
Since we have a moment or two before I need to cut this off, I will comment that the reason third derivatives are ignored, at least in dynamical laws for moving objects, is simply that when you work out the laws of motion, they only go as high as the second derivative. There's nothing further going on. Third derivatives can appear in physical systems where there's some activity such as rigid objects colliding, but those don't emerge from the fundamental dynamics.
Well, I would say that if you go in and you do equations and you assume, for example, a continuous space-time, if you assume conservation of energy, you will definitely get conservation of energy in a continuous deal. But if you don't make those assumptions, it's a whole new ballgame. Okay, so there's a question back there if we still got time for one more.
Last question.
Thanks. So I just wanted to confirm that, something that I agree with to a good extent, that the third derivative is essentially, you called it control. It's an ability to change from an acceleration to a different acceleration. And does that essentially point to free will or a lack of determinism? Is that what gives us the element of ability to have free will in life?
Yes, somehow I didn't actually use the word free will, did I? I just realized that. No, that's precisely what it is. The control, the third derivative would be, at least from Arthur Young's point of view, free will, and I think that's probably where it comes in. But it's that key. Earlier today, Mr. Hoke was talking about this wonderful work he did with spoon bending, and I have to tell you, I did one time. I had a spoon just like this, and then I was ready to go. It was it. And then, later on, I couldn't bend that spoon by myself, but it just did that, and it's just that real quick point. And somehow, there's a source of something that I'm getting energy from somewhere in the rest of the universe, and it worked. So, yeah, so that would be the free will part.